Beyond Earth, some worlds defy time itself. Imagine living on a world where the sun rises in the west, where daylight lasts for months, where shadows barely move across the ground, where a single sunrise could outlast an entire year on Earth. It sounds impossible. On our planet, time feels steady. A day is 24 hours. A year is 365 days. The rhythm is predictable. But not everywhere in the solar system plays by those rules. There is a planet where time itself seems distorted. On this world, a single rotation, one full spin on its axis, takes longer than the time it takes to orbit the sun. In other words, its day is longer than its year. That breaks intuition. We assume planets spin quickly. We assume they rotate faster than they travel around their star. After all, Earth completes one full spin every 24 hours. But it takes an entire year to circle the sun. That pattern feels natural. But nature does not promise symmetry. Somewhere in the inner solar system, there is a planet that spins so slowly that by the time it finishes one full day, it has already completed an entire trip around the sun. And that's only the beginning of the strangeness. Because this planet doesn't just rotate slowly, it rotates backward. The sun appears to rise in the west and set in the east. Its atmosphere moves faster than its surface. Its clouds circle the planet in days, while the ground beneath them barely turns. Time there does not behave the way we expect. And understanding why forces us to rethink how planets form, how they evolve, and how fragile planetary balance really is. This isn't just a curiosity, it's a clue. A clue about collisions, about gravity, about atmospheric forces powerful enough to reshape an entire world. A day longer than a year. It sounds like science fiction, but it's real. And the reason it happens may tell us more about planetary chaos than any other world in the solar system. Before we can understand how a day can last longer than a year, we need to define what those words actually mean. A day is simple in concept. It is the time a planet takes to rotate once on its axis. One full spin, from one sunrise to the next. A year is different. It is the time a planet takes to orbit its star. One full journey around the sun. On Earth, these two motions are completely separate. We rotate once every 24 hours. We orbit the sun once every 365 days. Rotation is fast, orbit is slow. That feels natural because it is familiar. But there is no universal rule that says a planet must rotate quickly. When planets form, they inherit angular momentum from the swirling disk of gas and dust that created them. Some spin rapidly, some spin slowly, some are tilted, some are nearly upright, and some, under extreme circumstances, can be slowed dramatically. In most cases, rotation remains much shorter than orbital period. Even massive gas giants spin quickly. Jupiter completes a rotation in under 10 hours, Saturn in about the same. Fast spin is common, slow spin is rare, but not impossible. Now, imagine a planet that rotates so slowly that one full turn takes longer than its trip around the sun. That means, if you were standing on its surface, the planet would complete an entire orbit before the sun returned to the same position in the sky. The orbital motion would outpace the rotation. And if that planet also spins backward, opposite the direction of most planets, the geometry becomes even stranger. Time becomes distorted. Sunrises are rare. Daylight stretches endlessly, and the sky behaves in ways that feel wrong. This isn't a trick of perspective. It's physics. And it happens because rotation and orbit are governed by different forces: initial formation, gravitational interactions, collisions, tidal effects, and atmospheric dynamics. On this particular world, something interfered. Something powerful enough to nearly stop its spin, to stretch its day beyond its year. And that's where the real mystery begins. The planet we're talking about is Venus. At first glance, Venus seems ordinary. It's nearly the same size as Earth. It's rocky. It orbits close to the sun. For centuries, it was called Earth's twin. But Venus hides one of the strangest rotational behaviors in the solar system. It spins backward, Most planets rotate in the same direction they orbit the sun. Counterclockwise if viewed from above the sun's north pole. Earth does. Mars does. Jupiter, Saturn, Uranus, Neptune all rotate in that same general direction. Venus does not. Venus rotates clockwise. That means if you stood on its surface and could see through the thick clouds, the sun would rise in the west and set in the east. This backward rotation is called retrograde rotation. And it immediately raises a question. What happened? Planets don't randomly reverse direction. Their spin is inherited from the original protoplanetary disk, the swirling cloud of gas and dust that formed the solar system. So, for Venus to rotate the opposite way, something must have interfered. One possibility is a massive collision early in its history. During the chaotic formation of the solar system, planets were constantly bombarded by large objects, protoplanets, smashing into one another. Earth itself likely experienced such a collision, one that created our moon. If Venus was struck by a large enough object at the right angle, it could have dramatically altered its rotation. It might not have flipped the planet upside down, but it could have slowed its spin to nearly zero, allowing other forces to take over. And that leads to the second strange detail. Venus doesn't just rotate backward, it rotates incredibly slowly. One full rotation takes about 243 Earth days. That is the slowest rotation of any planet in the solar system. To put that in perspective, Earth spins once in 24 hours. Mars spins in about 24.6 hours. Jupiter in under 10 hours. Venus takes 243 days just to complete one turn. And because it rotates backward, that 243-day period is measured relative to the stars, what scientists call a sidereal day. But the true strangeness appears when you compare that rotation to its orbit. Venus completes one full orbit around the sun in about 225 Earth days. That means its year, its full journey around the sun, is shorter than its day. Venus orbits faster than it spins. Imagine living there. If you could survive the crushing pressure and extreme heat, you would experience something extraordinary. By the time the planet finished one full spin, it would already have completed an entire year. Time would feel inverted. And because of the retrograde rotation, the motion of the sun in the sky would be slow and unnatural, drifting across the clouds over months. This backward, sluggish rotation is not just a curiosity. It's a fingerprint, a sign that Venus's history was violent. Something slowed it down. Something altered its spin. And that slow reversed rotation may be connected to everything else that makes Venus so extreme. Now we could say it clearly. On Venus, a day lasts longer than a year. But to truly understand that, we have to look at two different kinds of days. There is the sidereal day, the time it takes a planet to complete one full rotation relative to distant stars. For Venus, that takes about 243 Earth days. Then there is the solar day, the time between one sunrise and the next. Because Venus rotates backward and also moves around the sun at the same time, its solar day is different from its sidereal day. And this is where it becomes strange. Venus takes 225 Earth days to complete one orbit around the sun. But because it spins so slowly and in reverse, the time between sunrises on Venus is about 117 Earth days. That means if you stood on Venus, you would wait 117 Earth days between one sunrise and the next. But even that isn't the full picture. The rotation relative to the stars, the actual spin of the planet, takes 243 days. So from the perspective of its axis, Venus rotates more slowly than it orbits. By the time Venus completes one full spin, it has already traveled all the way around the sun. Its year is shorter than its day. This creates unusual patterns. The sun rises slowly in the west. It climbs painfully across the sky over the course of weeks. Then it sets in the east. Half of Venus' solar day, daylight, lasts nearly 2 Earth months. Then comes 2 more months of darkness. But unlike Earth, Venus's surface is not dramatically cooler at night. Why? Because its atmosphere is so thick and dense that heat is trapped efficiently. Venus is wrapped in a blanket of carbon dioxide, with surface pressure more than 90 times that of Earth. Clouds of sulfuric acid reflect sunlight while also preventing heat from escaping. The result is a runaway greenhouse effect, so extreme that the planet's surface temperature remains around 465 degrees Celsius, day or night. So, while the sky above may change slowly, the ground below remains relentlessly hot. The long day does not bring cooling. The long night does not bring relief. Time stretches on Venus, but temperature does not fluctuate the way we might expect. This slow spin also influences atmospheric dynamics. Because the surface rotates so sluggishly, the upper atmosphere has effectively decoupled from the planet below. High above the surface, winds whip around the planet in just 4 Earth days, far faster than the ground beneath them. The atmosphere outruns the planet. It's as if the sky has its own clock. Venus challenges our intuition about time, rotation, and climate. A day longer than a year is not just a mathematical oddity. It is the result of deep, powerful forces. Forces that reshaped the planet's motion and transformed its environment. And to understand why it spins so slowly, we have to look back to its earliest moments, because something dramatic happened to Venus, and it changed everything. Venus did not begin its life spinning this slowly. When planets form, they inherit motion from the rotating disk of gas and dust around a young star. That motion becomes rotation. Early Venus almost certainly spun much faster than it does today. So what slowed it down? There are 2 leading explanations. The first is violence. The second is gravity. Let's start with violence. During the early solar system, planets were not isolated worlds, moving peacefully in stable orbits. They were surrounded by debris, massive rocks, protoplanets, leftover building material from formation. Collisions were common. Earth itself likely experienced a collision with a Mars-sized body called Theia, an impact so powerful it created our moon. If Venus was struck by a large object at the right angle, the impact could have dramatically altered its rotation. Not necessarily flipping it upside down, but slowing its spin drastically. Imagine a spinning top struck sideways. Its motion wobbles, its speed changes. Now scale that up to a planetary level. A collision could have reduced Venus's rotation nearly to 0. Once slowed, other forces could take control. And that leads to gravity, specifically tidal forces from the sun. When a planet rotates, gravitational interactions with its star create subtle bulges in its atmosphere and interior. On Earth, tidal forces from the moon slow our rotation gradually over billions of years. Our days are lengthening, but extremely slowly. Venus is much closer to the sun than Earth. That means the sun's gravitational influence is stronger. If Venus's rotation was already slowed by a collision, solar tidal forces could have continued to drag on the planet's motion. Over millions of years, those forces could have pushed Venus into a slow retrograde rotation. But there is an additional twist. Venus has an incredibly thick atmosphere, about 90 times denser than Earth's. That atmosphere creates its own tidal forces. As sunlight heats one side of Venus, the atmosphere expands and creates pressure differences. These pressure bulges are pulled by the sun's gravity. Atmospheric tides can exert torque on the planet's surface. In other words, the atmosphere itself may have acted like a brake, or even a steering mechanism, influencing the direction and speed of Venus's rotation. Computer simulations suggest that once Venus's spin slowed below a certain threshold, atmospheric tides could have nudged it into its current backward motion. A delicate balance between solar gravity and atmospheric dynamics. The result? A planet that rotates so slowly it barely turns. A world where rotation and orbit nearly synchronize. A day longer than a year. Venus's slow spin is not random. It is the outcome of collisions, gravitational forces, and atmospheric feedback. It is a reminder that planetary motion is not fixed forever. It evolves, and sometimes it breaks the rules we expect. Of all the explanations for Venus's strange rotation, the the collision theory is the most dramatic, and perhaps the most intuitive. In the early solar system, nothing was stable. Planets were still forming. Orbits were shifting. Massive bodies crossed paths in chaotic trajectories. Impacts were not rare events. They were part of the process. We know Earth experienced one. The leading theory of our moon's formation involves a collision with a Mars-sized body more than 4 billion years ago. If that happened here, it almost certainly happened elsewhere. Venus, forming in the same crowded inner solar system, would have faced similar risks. A large impact could have drastically altered its rotation. If Venus were spinning rapidly in one direction and a massive object struck it from a particular angle, the force could have slowed its spin dramatically, even reversing it. You don't need to flip a planet upside down to reverse its rotation. You only need to change the direction of its angular momentum. Imagine a spinning wheel struck sideways by a heavy object. Its rotation can slow, wobble, or even reverse depending on the impact. On a planetary scale, the energy required is enormous, but not impossible. Computer models show that a sufficiently large collision early in Venus's history could have reduced its rotation to near zero. After that, smaller influences, like solar tides and atmospheric forces, could have determined the final direction. But there is a problem. Unlike Earth, Venus has no moon. If Venus experienced a moon-forming impact, why doesn't it have a satellite? One possibility is that any debris formed from such a collision eventually fell back onto the planet. Another is that the impact was different, powerful enough to alter rotation, but not to create a stable orbiting body. The collision theory explains the violence. It explains the dramatic slowdown. But it may not explain everything. Venus's rotation is not just slow. It is precisely slow, balanced in a near resonance with its orbit. And that suggests that after any impact, additional forces refined its motion. The collision may have started the transformation, but something else finished it. Collisions may have slowed Venus, but gravity may have shaped its final state. When a planet orbits close to its star, tidal forces begin to matter. Gravity does not pull evenly across a planet. The side facing the star experiences a slightly stronger pull than the far side. This difference creates a tidal bulge. On Earth, the moon creates ocean tides. Over billions of years, those tides slowly drain rotational energy from our planet. Our days are getting longer by milliseconds per century. Now imagine Venus. It orbits much closer to the Sun than Earth does. The Sun's gravitational pull is stronger. If Venus's rotation had already slowed, perhaps from an ancient collision, solar tides would have continued to apply torque to the planet. Over time, this could have nudged Venus toward a stable rotational state. Many close-in planets around other stars become tidally locked, always showing the same face to their star, like our moon does to Earth. Venus is not fully tidally locked, but it is close to something even stranger, a near resonance between its rotation and its orbit. For every 2 orbits around the Sun, Venus rotates roughly 3 times relative to Earth's perspective. Its slow retrograde spin may represent a balance point, where gravitational torque from the Sun and atmospheric torque from its dense clouds interact. And that atmosphere matters. Because Venus's atmosphere is so thick, solar heating creates large pressure bulges. Those bulges are also tugged by the Sun's gravity. Unlike solid tidal bulges in the crust, atmospheric bulges can shift more easily. Over millions of years, the interaction between solar tides and atmospheric tides could have stabilized Venus's slow backward rotation. It's possible that Venus was pulled toward this state gradually, like a spinning top slowly losing energy until it settles into a predictable wobble. The tidal locking mystery shows us something important. Planetary rotation is not permanent. It can evolve. It can slow. It can even reverse. Venus may be frozen in a delicate gravitational balance, not fully locked, not freely spinning. A world caught between forces. Venus's strange rotation is only part of the story, because the planet is not just slow, it is hostile. With surface temperatures around 465 degrees Celsius, Venus is hotter than Mercury, even though Mercury is closer to the Sun. The reason is its atmosphere. Venus is wrapped in a dense blanket of carbon dioxide. That gas traps heat extremely efficiently. Sunlight enters. Heat tries to escape. It cannot. Over time, this created a runaway greenhouse effect. If Venus once had oceans, and many scientists believe it might have, they would have evaporated as the planet warmed. Water vapor is itself a greenhouse gas. More vapor means more heating. More heating means more evaporation. A feedback loop. Eventually, the oceans would have boiled away entirely. Ultraviolet radiation from the sun would have broken apart water molecules in the upper atmosphere. Hydrogen escaped into space. Oxygen reacted with surface rocks. What remained was a dry, suffocating world. The slow rotation may have amplified this effect. Long periods of daylight would have allowed intense heating on one side, though the thick atmosphere distributes heat efficiently. But once the greenhouse runaway began, there was no return. Venus became a cautionary tale. A planet similar in size to Earth, possibly once temperate, now permanently transformed. Its long day and extreme climate are linked, shaped by early chaos and long-term atmospheric evolution. Venus is not just strange, it is what happens when balance is lost. Venus is not just an oddity in our solar system. It is a warning. When astronomers search for planets around other stars, they often look for Earth-sized worlds in the habitable zone, the region where liquid water could exist. But size and distance are not enough. Rotation matters. History matters. A planet can begin with the right ingredients and still end up unrecognizable. Venus shows us that collisions can reshape motion, that tidal forces can alter rotation, that atmospheres can spiral into runaway heating. Many exoplanets discovered today orbit close to their stars. Some are likely tidally locked, some may rotate slowly. Some may have thick atmospheres. Without understanding Venus, we might misjudge them. A world that looks promising from afar could hide extreme dynamics beneath its clouds. Venus forces us to rethink what Earth-like really means, and it reminds us that planetary evolution is fragile. One shift in rotation, one atmospheric tipping point, and time itself changes. On Venus, a day lasts longer than a year. The sun rises in the west. The surface barely turns. The atmosphere races overhead. Time behaves differently there, stretched, distorted, reshaped by collision, gravity, and heat. Venus reminds us that planets are not fixed machines. They evolve. They break symmetry. They fall out of balance. A world that may have once resembled Earth now spins backward beneath a crushing sky. A day longer than a year is not just a curiosity. It is a record of chaos, and proof that even time can be rewritten. What do you think? Comment and subscribe for more videos.